Hello and welcome. My name is Ian, and in this video, we're going to be taking a closer look at some theoretical probability distributions, including some common distributions that arise often in scientific work. And to start off, we kind of go back to this original idea of a probability distribution. Before that, we introduced this idea of a random variable, and a random variable is going to represent possible events. The relative proportions of those events, those outcomes, are where we get probabilities. So in the previous video, we looked at the 2 dice throw example, and we enumerated all the possible outcomes. And that allowed us to compute directly probabilities for those different categories of outcomes. And then we showed how this is the case for different generating processes, and that you can have a corresponding probability distribution. And it might not be that you always are able to enumerate the different possibilities, but you nevertheless have an underlying distribution that you could sometimes explore using experimentation or the Monte Carlo method. And so probability distributions, so probabilities in general obey these basic axioms, right? They need to be a number from 0 to 1. They need to be additive. If you have the probability of x1 or x2, then that should be less than or equal to the probability of x1 plus x2, probability of x2. If you sum up all of the different probabilities, they should sum to 1, because this represents all of the possible events in your space. So if we kind of get into some of the differences between different probability distributions, it's useful to start thinking about discrete and continuous again. So if we recall with random variables, you could have discrete random variables, and these would be for countable processes, things like the number of heads that you get from 3 coin tosses, for example, versus continuous random variables. So these could be things like the length of some object or the volume of some liquid in a tube. And unlike like bar charts, if we had a histogram had information on both the x-axis and the vertical axis, and this was true both for continuous distributions, but this is also the case for discrete distributions. And so like with data and histograms, a probability distribution can also be discrete or continuous, and we have a corresponding distribution diagram that's very similar to the histogram or the frequency distribution visualization that we had for data. But then this is going to correspond to our event space. And so this is often called the probability mass function. And we think of this as the set of probabilities for the space of different events that we have. So we mapped this out when we enumerated all the possible results you could get for the 2 dice throw. And the only thing we're adding here is the value on the vertical axis here has to be this probability value here. So this is the probability that our random variable x takes on a particular value, little x here. And so as with data, which can be continuous or discrete, probability can also be continuous, discrete. So we have the analog of the probability mass function, which is the probability density function, and then this is going to apply to continuous random variables. And so instead of probability on the vertical axis, we have a probability density function, f of x here. And you can see it's a smooth curve because it's continuous. And we said this was the case for random variables as well. If you want to talk about probabilities for continuous quantities, you have to think in terms of ranges. So for any one point, if I were to pick a point x here, the probability for that point is going to be 0 always. And that's because there's an infinite number of points. So if any of those points had anything less than 0, then we would have a total probability that is going to be infinite as well. Therefore, we talk in terms of ranges. So I would ask you then instead, what's the probability that x falls within some range a to b? And if we have a function, a probability density function, then it's going to be the area under that function, under that curve, or the integral from a to b of our function, that's going to give us that probability value. So we're integrating from a to b, and then it's like, we're taking like basically the height times this range here for many kind of infinitely thin slices. So we've also talked briefly about different kinds of means. So for weighted or for binned data, right, we had this method we could use to compute the mean, which was a bit different from the traditional arithmetic mean that you calculate by just adding everything up and dividing by the total number of points. Instead, we would multiply the heights of bins times the values of those bins, and then divide by the total number of points, and that would also give you the mean. So we have something very similar for probability distributions, where in this case, the height is not going to be a count, but it's going to be a probability. And if we multiply the probability of every bin, if in the case of continuous variables, maybe infinitely thin bins, we're going to multiply these together and sum them up, and then that's going to give us a mean as well. And so this is sort of like the case for, if we're talking about a discrete variable, this would be like, we do an infinite number of dice rolls, right? The law of large numbers, we're not taking the mean of a limited sample of our data set, but this is sort of like the perfect mean, the ideal mean. And we'll represent this quantity with the Greek letter mu. And this is also referred to as the expectation or expected value. So expectation, you can think of as kind of generalization of the mean, and it's one that applies to distributions, probability distributions. And so this is, again, just the equation from the previous slide, but here we kind of visualize this. So if we have a probability mass function here, so this is a discrete variable, and we have different results, maybe this is like the dice throw or something, and the height of these different bins here indicates the probability. If we do this for each of the possible bins here, we multiply these heights, the probability times their values, and then sum those up, and we're able to get a kind of expected or population mean from this probability distribution here. And so we have an example here. So this is a probability distribution representing the probability that we observe a particular mass of a protein if we were to sample a random molecule from the mixture. And so what we want to know is, what is the average mass that we could expect if we were to sample many molecules? So here we have molecular weight, size of the protein on the horizontal axis. And then again, the heights are going to be the probabilities here. And so this is a probability distribution. This is not data, but this is instead representing the ideal kind of theoretical set of possibilities. And what we want to know is the expectation, or what's the population mean for this distribution. And one way you can kind of imagine this or intuitively figure out what is expectation value? What is this equation doing? Imagine we could just chop this thing up into pieces. So here we've taken, this bar here, the 70 bar, I've chopped it up into 4 pieces, and I've chopped the 60 bar here into 3 pieces. And if we imagine then these are like the weights, 70, the molecular weight is 70 for this thing here. And imagine I just had a scale and I could weigh these. And if I did this, I could get an average weight here. If I weighed all of these things, we would take, we have two of these guys who are 50, and there are 12 possible values. So, right, the probability is going to be 2 of these out of 12. We have 3 out of 12 that are 60. We have 4 out of 12 that are 70, and 2 out of 12 that are 80. And in each of these cases, I'm multiplying the weight by how much of them there are. This you can imagine, this is if I wanted to know just the average weight of these heavy objects, these different objects, this is how I could compute the average weight by just totaling them up according to their size and then dividing by the total number here. So this is kind of what's happening sort of under the hood when you do expectation value, or when you get the mean of the population here. You're multiplying the values times the probabilities, summing them up, and that's giving you an average in exactly the same way that we did here. In this case, 63 kilodaltons. So for this population, this particular distribution here, if I ask you, what's the average molecular weight of a protein in this population, this would be the answer, 63. Okay, so that was discrete. But what if we want a continuous variable? So it's not going to work then to multiply the heights of bins with their bin values, because we no longer have a countable number of bins. Instead, we have a continuous curve, but we can do the analogous approach to a summation for a continuous variable, and that's integration. So the expectation for a continuous random variable looks like this. We have an integral where we have inside the integral is going to be the value x here on the horizontal axis times the height, the probability here. And we're going to do this from minus infinity to infinity. So we're going to integrate the entire curve and basically just get the area under this curve, but weighted according to its value. So the larger the value, the greater the contribution to this value we're going to get here. And this makes sense, right? So if you have, say a particular distribution of heavy things and light things, and I ask you, what's the average weight? Well, the heavy things are going to contribute more to that average weight than the light things. So you need a lot more of the light things if you want to, say, have balance them out. So why is this important? Why do we want to know about distributions? Well, it turns out that some of them are very well-studied objects, and it's going to be useful for us to know a thing or two about some of the really commonly occurring distributions out there. They have these generating processes that are well-studied and well-known. And what makes them useful is that they're models, right? They're models of reality, and they describe in kind of explanatory terms what is going on or what is taking place. And we can use a histogram to look at our data and visualize it, but that doesn't necessarily describe what's generating it. And knowing about probability distributions is kind of applying an explanation in addition to we're not just describing the shape, but we're describing the process with the probability distribution. And so you can often fit data to known probability distributions. And when you do that, it's like you're modeling your system. And so because it's good to know about some of the more famous ones, we'll go through them now. And so we'll talk about the binomial distribution and the Poisson distribution in this video. And then later we'll also talk about Gaussian distribution or normal distribution. But the thing to realize is that there are a lot of distributions out there. So we'll kind of maybe discuss some of these briefly. But you have different names for them, things like the Pascal or the geometric distribution, the Boltzmann distribution. And these all describe different generating processes and they have different shapes. Some of them look very similar to each other, but what distinguishes them is the way that they're generated and the origins of that shape. So we'll start with the binomial distribution. And this is an example of a discrete distribution. And this is going to describe the probability of a certain number of successes when you have multiple trials with just two possible outcomes. And so usually we talk about successes and failures. So the outcome of a coin flip could be heads or tails, but in binomial distribution vocabulary or language, we would talk about successes. So we might define, say, a heads outcome as a success, for example, or we could define tails as a success. And then what we have is a probability. So this quantity P here is going to be the probability of, say, a heads or a success. And we can use this P value to represent, for example, a bias coin as well. So it doesn't have to be 0.5, we could say it's 0.3 as well. We'll do multiple trials. So this would be like multiple coin flips, and some of those results are successes, some of those results are failures. And because this is such a simple and basic process, it tends to appear in all sorts of useful places. And so one example is if we're talking about or thinking about DNA sequences. DNA sequences, if we're sequencing them or we're reading them, often we'll have a read error associated with that process. And that error might be very low. So we could have a sequencing machine, and for every base that occurs in the DNA sequence, we have, say, an independent chance that a substitution error occurs, 0.0001 probability, we could say. And so again, just like the coin flip, we have two possible outcomes: error or no error, success or failure. We could define in this case success as an error occurring, and then the binomial distribution function. So this is going to be an equation that tells us about the shape of the space of different events that you can get for this process. This is going to then apply to this DNA sequencing problem. So here's a very practical example if you're a life scientist. So not everything has to be in terms of dice and coin flips. Another example is, say, a population of cells. And we might say, each cell has an independent chance to express some gene, and that chance given by this probability, 0.01. And once again, we have two outcomes: express or don't express. And if that's the case, maybe cells can be a bit messier. So this may not necessarily always apply, but we can imagine a situation where this could be true or mostly true. And once again, binomial distribution would represent this process. So what does it look like? So this is a probability distribution described by an equation. So we have an analytical expression here. And the idea here is that this is a well-studied process of functions. So the reason we have an analytical expression here is because this is a known and heavily studied process. And there are certain distributions out there that are like this, known animals, where we know absolutely everything there is to know about them. And so because they're so common, it's very useful to have all this information about it. And the binomial distribution is defined in the following terms. So we have these different parameters. So one of them is the number of successes k. So I might be asking a question, what is the probability that I get 3 errors in my sequence or 1 error in my sequence? So that's going to be k. We have the number of trials. So this is the number of coin flips, or if we're talking about the DNA example, this could be the number of bases. So I'm going to check 1,000 DNA bases, and I want to know what's the chance that there are 3 errors. K equals 3 errors. So n is going to be the number of bases in that case. And then we have the probability of a single success. So for one trial, what is the probability of the event we're interested in? That's P. And then the converse of this is going to be, or the complement of this is going to be 1 minus p. So if p is our probability of success, then our probability of failure is going to be 1 minus p. And that's, of course, because of this condition of the normalization condition of probability, which says that everything has to sum to 1. And then this is the equation. So we have here, everything is in terms of these 3 variables, k, n, and p, you'll see. This exclamation here, this is the factorial, right? So factorial 4, that's going to be like 4 times 3 times 2 times 1. And then this expression here is the combination expression you may recall from combinatorics. But the main thing to note here is that we have absolutely everything defined here. So this equation gives us p, right, for a given number of successes, for a given number of trials, and for a particular value of p. And that means we could compute this distribution, the shape of it, by solving this for any number of, say, k successes. If we want to know, what is the probability of certain number of successes, we can evaluate this function, and we don't need to do Monte Carlo sampling, for example. We have an analytical expression in this case. So these are just some examples to get some intuition. We have, let's say, p equals 0.5, n equals 4. Then we have on a horizontal axis, what's the probability of 0, 1, 2, 3, or 4 successes? So if we only have 4 trials, then we're not going to go above 4 in that case, right? Like we can't get 5 successes if we only flip the coin 4 times. So that's immediately going to define the range here. But then the heights here, how do we get the heights? So it's evaluating this expression here that we have on this page. And you can do that again. So what about n equals 15, right? We can solve this for n equals 15, but here, let's say p equals 0.1 instead, smaller. So we're going to have a distribution that looks like this, or p equals 0.8. So here's the same number of trials, n equals 15, but now p equals 0.8, and we're going to see the distribution is skewed to the right in this case. And what's handy about these known distributions, like the binomial distribution, is that mathematicians have already solved for a lot of the important quantities we're also interested in. So the expectation value, right, that's the mean, this generalized version of the mean that we discussed. We could go through and solve it for each of these cases, but we actually already know this. So there's an analytical expression that we have for the expectation value, or the mean, the population mean here, and it is n times p in the case of the binomial distribution. We also have the same for the variance and standard deviation. So we have an exact equation that describes the population standard deviation for a given value of k and p. So that is a very useful thing, and a reason why it can be good to know if your process is a binomial, it applies to the binomial distribution. So here's an example. Let's say we're processing next-gen sequencing reads from an Illumina experiment, and each base is 300, each read is 300 bases long. So we have a DNA strand, it's 300 bases long. And let's say we produced this DNA using PCR, and we used a particular polymerase which has a substitution error rate of 0.01 errors per base, or probability of an error per base. And we want to know, for a given read, if I pick any one of these reads, 300 base long reads, what is the probability that there are 3 errors? And so this may not immediately jump out at you as something equivalent to flipping coins. But if we look at it, we have everything we need, right, to apply the binomial distribution equation. We have a probability for a success or failure. So only 2 possibilities, 2 outcomes. Either there's an error or there isn't an error. We have a number of trials. So there's 300 bases in each of these reads. and we have a probability of that success, P. So we just go back to our expression here, fill in all the values that we have, and solve for P, and that gives us an exact value. And we can do this for different values of K or different values of P. We could also define this problem differently. So, we could define the problem, for example, let's say we want to know what is the probability that there is a certain number of bad reads with errors in, say, a sample of 100 reads. And then we would want to know our probability that any particular read has one error in it, or at least one error. So that would be a different case. So then a trial, then instead of being a base, a trial would be a read in that case. But as long as we have this setup where we're dealing with successes and failures, and we have a probability of that, then we can apply this binomial distribution. What about another process? So we can talk about the Poisson distribution. So this is another extremely common scenario or natural process that occurs all the time. And this is another type of discrete distribution. And this is going to apply to any case when you're counting events in some kind of interval. And an interval here can be almost any continuous variable. So often we talk about events occurring within a time interval. So it could be buses arriving, in an interval, say 10 minutes, I'm at a bus stop, and for every 10 minutes, how many buses arrive? This could be described with a Poisson distribution. But we don't necessarily need to talk about time. So the interval could be an area as well. So we could be talking about lightning flashes and how they're distributed over a city. And then our interval might be, say, a square kilometer. And so I want to know how many lightning events there are in a square kilometer. And you could also apply this to volumes as well. So, number of snowflakes in a volumetric cube of some kind, or ants occurring along a leaf stem. So there, the interval is a distance in that case. So there are many manifestations of this process that superficially seem very different, but all of them amount to the same thing, counting events over an interval. And in this case, we have another distribution function here to describe this. And instead of n, p, and k, we have the parameters here, k and lambda. And k is going to be the number of events. So we might be asking the question, what is the probability that there are 5 lightning flashes in a square kilometer? Lambda here is going to be the average number of events for one unit of our distribution. And often you'll see this kind of simplified to be in terms of, say, a particular interval of time and a particular rate. So I might tell you there are 10 lightning flashes per square kilometer, or 3 buses per minute. So in this case, we would use that, multiply 3 buses per minute times 1 minute to get our rate here, or our average number of events, lambda. And then once you know these things, you have an equation, right? So we can compute the probability for a given number of events. And then, so here's another example. So, let's say lambda equals 1, and we can compute for k equals 0, 1, 2, 3, 4, 5, like this. The probability then is going to be the heights of these values for particular values of k. If lambda equals 2, then we're going to start shifting to the right here. Lambda equals 5, shifting even more like this. And just like the binomial distribution, we have these handy already solved properties. So the lambda is going to be our expected value, our average. The variance here is going to be Also lambda, or the standard deviation here, is square root of lambda. So again, these are solved quantities that allow us to skip the step of needing to sample this distribution because it's so well studied that we already know everything there is to know about it. So here's an example. We have streptavidin molecules immobilized on a glass chip, and we have a certain density of 10 molecules per square micrometer. And we want to know, in a patch of 10 square micrometers, what's the probability that there are 80 molecules? So a way to picture this is we have, different square micrometers, and a square micrometer might have a certain number, 1 event or 6 events. And on average, we have this number 10 here. So we can compute our lambda, right? That's the rate times the interval, r times t, to get 100. And then the question asks us, what's the probability that there are 80? So k equals 80 in this case. We just plug these into our equation and solve for the probability then. And there are other distributions out there. So Poisson and Binomial are very well-known ones, but there are other animals out there, and it's maybe just useful to know that these exist. So for example, the Pascal distribution is going to be the probability that it takes X number of trials to reach K successes. The geometric distribution, that's going to be the number of trials until a success. You also have the exponential distribution. There's another really common one. And this is related to the Poisson distribution, but this is actually a continuous distribution. And it's going to be the time between events. So in the example of buses, instead of talking about how many buses are there, in a 10-minute interval, we might ask, how long do you have to wait between buses? And then that's going to be described by an exponential distribution. You also have the Erlang distribution. So this is going to be similar to the exponential, but it's the time between K events. So instead of just one event, we might say, how long would you have to wait for 3 buses to pass? So those are some basic distributions. And then in the next video, I will talk about the Gaussian distribution and the normal distribution. And that's another type of continuous probability distribution. But this is a bit of an intro, and these are some of the most common ones that occur in nature and in general. And it's good to know about them simply because you will run into them all the time. The fact that we know how to solve for these things exactly and analytically is an advantage. It means we don't need to use the Monte Carlo method to discover the shape of the distribution. If we know the process, then we already know the shape, basically. And that's all. Bye-bye.